Applications of aqueous equilibria. This is actually part of chapter 16. The solubility products are called KSP, so you're going to hear me refer to that phrase a lot. I tagged this on to the end of this chapter because it's so similar to all of what we do in this chapter. So let's go through it. KSPs are for slightly soluble substances. As the salt dissolves in water and ions are released, they can collide, reform the solid. Equilibrium is reached when the rate of dissolution equals the rate of recrystallization. And again, these are usually made for slightly soluble substances. A saturated solution means when no more solid can be dissolved at equilibrium. So a solubility product is just like our other K values. If it's a solid, it's not going to be included. That's why we're going to leave it out. And so it is going to be calcium, the concentration of calcium times the concentration of fluoride squared because of the coefficient of 2. And then adding more solid will not affect the amount of solid that can be dissolved at a certain temperature. It'll just hang out at the bottom, so that won't make a difference. And it would increase both reverse and forward reaction rates because there is a greater amount. Now, these KSP values are in your appendix, so make sure that you're checking that. So that's where this page comes from. I want you to look at how small some of these numbers are. I mean, you've got 10 to the negative 32, 10 to the negative 38. So this is what I mean by slightly soluble substances. Of course, these have a lot of ions, and that affects that value. And some of them are as large as 10 to the minus 5, but they're usually the ones with just 2 ions in them. Here's an example problem. Copper 1 bromide has a solubility of 2 times 10 to the minus 4th molarity at 25 degrees Celsius. Find the KSP value. The solubility tells us the amount of solute that can be dissolved in 1 liter of water. So we're going to use an ice table here. And we have copper 1 bromide is breaking down to 1 copper 1 and 1 bromide ion. Of course, we don't have any initial ions. Then when it starts to dissolve, this told us how it dissolved. And so we know the ratio is 1 to 1. And so it is going to be that value squared to get the KSP value. The KSP value for copper 2 iodate is our next question. So that's going to have 3 ions in it. And so that's going to affect it. You could take 1.4 times 10 to the minus 7th. It's giving you the KSP value in this case. And you're solving for X here. And so you're going to have X and 2X quantity squared. So you're going to end up with 4X cubed in the numerator. And there is no denominator. So you're going to take the cube root of the KSP value, and that tells you that the concentration of copper 2 is going to be 3.3 times 10 to the minus 3rd, and this is going to be 6.6 times 10 to the minus 3rd. That would be double the amount. Comparing solubilities. You can only compare directly KSP values for compounds using the same number of ions. So notice that each one of these, there's 1 calcium, 1 sulfate, so 2 ions total, 1 copper, 1 carbonate, 2 ions total, 1 silver, 1 iodide, 2 ions total. And so we can certainly tell that calcium sulfate is much more soluble than silver iodide, and that copper 2 carbonate lies in between there. Why can we use KSP values to judge solubility? Because it judges how the value changes. And again, if you have different number of ions, you're going to end up with squared values, cubed values. And so you'd have to take that into account in your answer. And you're going to see where we're going to do that a little later on. And so you can only compare actual solubility values of X when the compounds have different number of ions. So here is an example of that. You have copper 2 sulfide, which contains 2 ions, 1 copper, 1 sulfide. And so you're going to take the square root of its KSP value to get its solubility. Silver sulfide has 3 ions, so you're going to take the cube root of that value and get its solubility. And the next one has 5 ions, so you're going to take the 5th root of that value. So you can see it is actually, the ions are more soluble individually in that. And so keep that idea in mind. Now we're going to look at how the common ion affects KSP. Obviously, the solubility of a solid is lowered when the solubility already contains one of the ions. Why is that? Well, let's take a look at a reaction. If you increase the amount of a common ion, it's going to drive the, Le Chatelier says it's going to drive the equilibrium to the opposite direction. And so that's why we can say that. So this one's asking us to find the solubility if we have 2 salts mixed together. And so you have this strong, very soluble salt. So all of this is going to go into solution. And this is only slightly soluble with this KSP value. So this is how we would work out this problem. You have 0 calcium, but because of the strong salt, or the soluble salt, being present, it's 0.025 molar there. And again, I have to have a 2 here because of the coefficient. And so I'm using the coefficients in front of my x values, and I do that. And so my KSP value is equal to the calcium ion times the fluoride ion squared. The KSP value is absolutely teeny. So yeah, I can get rid of the x's here. This is not going to be important. So I'm going to have x times 0.025 quantity squared is approximately equal to the KSP. And so I solve for x, which then in turn would mean that this is 6.4 times 10 to the minus 8. And then you would double that and see if adding that, which you can tell significantly, anything to 10 to the minus 8 added to that is not going to change that significantly. pH and solubility. If you're talking about something that is an acid or a base, and you're adding basicity or acid ions, then you're going to drive the solubility. It's going to become less soluble. That's how it would happen. And so this one's an example of a base. So if you add hydroxide, again, that drives the solubility that direction. Now it's talking about what if you have just a regular salt, and which one is the acid going to attack, or which one is the hydroxide going to attack? Well, the acid's going to attack the cation. I'm sorry, the anion. I said that wrong. If the acid is going to attack the anion, that's the sense of removing it, because it's going to form phosphoric acid, and it's going to make it shift right to replace what was removed. So it's going to go right to replace what was removed there. So you have homework to complete. I'm going to go ahead and put that on a Google Doc for you. Again, don't forget to copy and paste that Google Doc. That is such an important step. If you don't do that, you will lose all your work and be very frustrated.